Hello everybody, in this video we're going to look at how we can minimize numeric errors when we're writing programs. So to demonstrate this, we're going to use a for loop that increments a floating point number. Now we're going to compare the following cases. We're going to use a float as the counter variable, a double as the counter variable, and an integer as the counter variable. Now the goal of this is to minimize the errors caused by the limited precision of floating point numbers. So over in Eclipse, I've created a new project and we're going to add a class to this called test_sum, and we'll get Eclipse to create a main method for us. So in the main method, we're going to do the following. First, we're going to create a floating point data type called sum, and we're going to initialize it to 0. Next, we're going to have a for loop. So the keyword for, and now we're going to have our assignment in here, or our initializer statement, and we're going to have a float called I, which is going to start off as 0.01 f. We put f here to say that this is a float type. Next we have a semicolon and our conditional, and we're going to loop until I is either equal to or greater than 1.0. And again we're going to put an f here. Finally, what we're going to do each time through the loop is we're going to add 0. We're going to say I is equal to I plus 0.01 f. So we're adding 0.1 to I every time through the loop. Now, what's next? Well, inside the loop, we're going to have the following. Sum is plus equal to I. So each time through the loop, we're going to add whatever I is currently equal to sum. And then we're going to, at the end of the loop, once we've finished, we're just going to print this out. System.out.println the sum is, and then we're going to tack sum onto the end of that. So this is our simple program. Now what we should expect is if we work out, if we're starting with I equal to 0.01 and we're adding 0.01 onto it each time, and we're looping until I is greater than 1, what we should end up here is sum being equal to exactly 50.50. But if we run this program, run as Java application, I forgot a space here. Let's run that again. Sum is 50.499985. What went wrong here? Well, the problem is that floating point numbers are imprecise. We can't represent a number exactly with a floating point number. So the problem is that we just don't have enough bits inside our floating point variable to store this number. So what we can do is change this to a double. And we can also change I to a double as well. That gives us 64 bits of precision now instead of 32, which is what a float is. So if we run this now, so remember what we got here. Actually, I'll put it in a comment so we can keep track of it. When it was a float, we got this. Oops, 85. Let's run this again now that we've got doubles. We got closer, but it's still not right. What's going on here? Well, the problem is that if we printed this all out, again, we've got a precision. We've got way more digits here, so we get a more precise answer, but it's still not exactly right. A better way of doing this is to use an int here inside the counter. So what we're going to have here is two variables now. We're going to store two doubles. So double current value equals 0.01, and we're going to use an integer in our for loop. So if we work out what this is going to do, going from 0.1 to 1, this means that the loop is going to execute 100 times, or it should execute 100 times. The problem when we're using floating point types is we can't guarantee this because we don't know whether I is going to ever equal exactly 1.0f. So a better way is to use an int. So int I, oh, actually we'll call this count. count equals 0. Count is less than 100. Oops. Count plus plus. So this is a much simpler loop. We're just using an integer type, initializing it to 0 while we loop while it's less than 100, and we're incrementing it each time. So we're still going to loop exactly 100 times, but because integers can represent numbers precisely, although they can't represent decimal places, we know that this will execute exactly 100 times. So we're just going to modify this slightly. So we're going to increment sum by current value. And then we're going to current value minus, I set this to the wrong value. Oh no, I didn't. Plus equals 0.01. So this is kind of the same functionality as what we had before, except we're using an int in our for loop. But really, we're still adding the same data onto sum each time. So let's save this and run it again. Oh, way closer. So the problem was last time is we didn't actually execute the for loop 100 times because of the imprecision of using I as a double. So we didn't get exactly the right number. But we're getting closer. So int count, we got that, which is still not exact, because remember, we can't exactly represent 50.50. We might not exactly be able to represent 50.50 as a double either, but we're getting a lot closer because we guaranteed that our loop executed 100 times. Now, as a final kind of demonstration here, we're going to start off with current value equal to 1.0, and we're going to decrement this each time. So really, this should be the same. Instead of incrementing current value each time up to 1, we're starting at 1 and decrementing it each time. So in theory, if we could represent numbers exactly, we should get the same. We should get the same answer. So let's run this again, and you can see we didn't actually get the same answer. So this is decrementing. We ended up with that. Now, the reason for this is because adding from big numbers to small numbers is less accurate from going from small to big. So we actually, by decrementing like this, we actually get less precision than going up like we were before. Now, the moral of this story is that we have to be really careful when we're dealing with floating point numbers, whether they're double or float. So remember that double gives us twice as many bits to store a number as we do for a float, but it's still a floating point number, which means we're still limited by the precision that we can have. So it's really important to keep that in mind when we're writing programs. And something that really comes up, if we have double A, B, if we have two doubles and we have some comparison, if A is equal to B, it's possible that they are not absolutely equal, but they're really, 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 really close. So another way of doing this is to test for some tolerance. Whether A minus B is less than whatever tolerance we're going to use is something that we often have to do when we're dealing with floating point numbers. So just to summarize, floating point arithmetic is imprecise. We only have a limited number of bits available to store a number. Now, a float uses 32 bits and a double uses 64. We shouldn't rely on floating point numbers when attempting exact Boolean operations such as the equals operator, because it might never be equal exactly, which is what the equals operator expects. So it's also a good idea to use integer data types for iterators inside loops, because it guarantees that our loop will execute as many times as we're expecting. So this video was just kind of, not a warning, but something to keep in mind when we're writing programs, that we really have to be careful when we're dealing with floating point numbers. So that's it for this video. Thanks a lot.